All right, so I wanted to give you a sort of overview of what we're doing on the the Kepler's third law lab. And I've pulled the tables out of the lab write-up that you can see. These are what's included in the module in eLearn. And we'll just show you where the numbers came from and how you go about doing the lab here. So the idea is that you want to do like Kepler did back about 4 centuries ago and figure out the relationship between the size of a planet's orbit and the time it takes to go around the sun. Now, life is easier if we use astronomical units for the size of the orbit, because Earth's orbit is 1 astronomical unit. And if we use years for the time it takes to go around the sun, because that's 1 year for the Earth. And so all of the numbers for the Earth are ones, right? Because 1 squared, 1 cubed is all 1. And then when we make any ratios for the Earth, it's going to be 1 for whatever the ratio may be. And so really what we're looking for is for some ratio of all the other planets to have 1 as well, right? If we're using these R's and T's and astronomical units in years. So let me kind of show you where these numbers in the first table come from. If we go to the textbook, we can look up the size of the orbits for the planets that are in the table here, just from the appendix or from the solar system chapter. And we get these values like Mercury's 0.39 astronomical units from the sun and on like that. And we can also look up the time it takes them to orbit. It takes Mercury 0.24 years. It takes Venus 0.62 years. It takes Mars about 1.5 years. You'll get those numbers here. And so where we get these numbers from is from taking these numbers and raising them to the particular power. So for Mercury, for instance, if we take R squared for Mercury, here, there we go, which means I'm going to take the 0.39 and multiply it by itself, right? 0.39. Do that on your calculator, you get 0.152. So that's where this number here comes from. And then the R cubed, that's from taking that same 0.39 and cubing it. Which remember, when you cube something, that is to say it times itself 3 times. So 0.39 times 0.39 times 0.39. And that, if you work that out on your calculator, is 0.059. Right, so that's this number right here. The same thing with the t squared. If you take 0.24 and square that, your 0.24 squared, or 0.24 times 0.24, that gives you 0.0576. Like that, right? And the same thing, if you found the t cubed, you could find that number. It's 0.24 times 0.24 times 0.24 and fill that in. And you want to go back and fill in all of this. Once you get the R and the T for the different planets, fill in all of this table for all of the planets. Again, the R cubed is going to be taking this number and multiply it by itself 3 times. So for Venus, you get R squared by taking 0.72 times 0.72, that's 0.518. You get the R cubed by taking 0.72 times 0.72 times 0.72, like that. And then for the t squared here, you take 0.62 and square it, 0.62 and cube it, goes right here, and so on for the other planets. Okay? Then you want to look at these different values for the powers of R and T, and much like Kepler did, you want to see if you can find a ratio that is the same for all of the planets. Now here, what I've done is I've done a couple of them for you, and I'll show you where these numbers come from. So like for the R to the first over T to the first, what I'm doing is I'm taking the R to the first for Mercury, which is 0.39, and the T to the first, which is 0.24, and I'm dividing those, right? So if I take R to the first over T to the first for Mercury, that's 0.39. Divide that by 0.24, and that is equal to 1.625. Right? So let's take in this number and divide it by that number. Okay. Do the same thing for Venus. Take 0.72, divide it by 0.62, you get 1.161. For Earth, it's 1 divided by 1, which is 1. And then the same thing for Mars, Jupiter, Saturn, fill that in. Okay, so this clearly is not the one that is the same ratio for all of the planets, right? Again, for Earth, the ratio is going to be 1, so it would need to be 1 or close to it, 1.02 or 0.99 or something like that for all of the planets. Okay, so that's not going to work. So let's try another one, R squared over T to the first. So let's see where that number comes from. For the R squared over T to the first, what I'm doing is I'm taking my T to the first value, which is the 0.24 here, I'm going to divide that by divide that into the r squared, which for Mercury is the 0.152. Right? So I take r squared over t to the first is 0.152. That's the value for r squared for Mercury. Divide that by the t to the first for Mercury, which is 0.24. And if you do that on your calculator, you get 0.633. And so that's where that number comes from. If you do that for the rest of the planets, you can fill in that column there. We also know this one's not the right one because it would have to be 1 or really close to 1 for all the planets. It's not for Mercury. So there's a different ratio. These question columns here, you're going to do this same process, but with different pairs of r's and t's. So you might try like r squared over t cubed and see what you get, or r squared over t squared and see what you get, or r cubed over t squared, whatever you may be. So fill in these columns on your data sheet with different ratios until you find the ratio that's going to be 1 for each one of them. Now, one of the things you can do is you can kind of look at the columns and see which r's and t's are the same thing. Let's say you got t squared and r squared, probably not going to work because it's 0.1 and 0.05. If I divide those, that's not going to be 1, like it's going to be 1 for Earth, right? So you can kind of give yourself a clue if you look at what column for the r's here matches a column for the t's here, right? So you'll find, and if you really get stuck, you can go back and look in the chapter and see what is the ratio, the powers, what power of r and the power of t in Kepler's law from the textbook, and that can give you a clue there. Right? So that's the main part. You'll identify that ratio and you'll find, and then you can give that ratio on the data sheet. Let me say just for, just suppose that it was r to the 4th over t squared, okay? Now it's not gonna be that, but I just want to use this for illustration purposes, all right? So we know that that would be equal to 1 because it's going to be equal to 1 for the Earth, right? And so what this tells us for all of the planets, whatever the ratio is, in this case, for example, it's r to the 4th over t squared, is if that's equal to 1. In order for that to be equal to 1, then we would know that the t squared number has to be the same as the r to the 4th number to divide them and get 1. So this would tell us that t squared is equal to r to the 4th. Again, that's not right, but we're just using that as to work with the rest of the lab here for a minute. So what you got to do in the second part of the lab is once we know this ratio, we're going to look up the radius for Uranus and for Neptune and for Pluto. Right? Pluto may be a little bit hard to find because it's not a planet. You may have to just get online and look for that if you can't find it in the textbook. But you want to get the radius, their semi-major axis in astronomical units, and then use that to find the period here. Okay? So let's suppose this was the ratio that worked. Again, you would have a different ratio, but supposing that's right, let's go through this process. So for Uranus, you look it up and its R is equal to 19.2 astronomical units, okay? And so what this is telling us, if this were in fact the ratio, it would be telling us that the period squared for Uranus is 1.92 raised to the 4th power. So 19.2 times 19.2 times 19.2 times 19.2, not 19.2 times 4. So just to plug these in, if you do this to the 4th power, you can check my math here. It's 135,895 and some decimals after that, but I'll round it off with that. Okay. So whatever the ratio that works, you're going to take the R for Uranus, raise it to that power, and that's going to be equal to T to whatever power it happens to be. In this particular case, I know that, well, I'm pretending that T squared is equal to this number, which is the R to the 4th power. In this case, if I want to find the T, the way I get T from T squared is I take a square root, right? And to make sure you know how to take the square root, you can check the math here on this one. This would tell us if this were in fact Kepler's law, that you take the square root of 135,895, you get 369 years. Now that's not the orbital period of Uranus. It's around 80 something years, if I remember right, something like that. But this is the process you would go through. Again, find the ratio of the R to some power to T to some power that gives you a constant, which would be really close to 1 for all of the planets. And then that's going to tell you that that power of T equals that power of R. And for Uranus, Neptune, and Pluto, look up the R that you've got, raise the r to that power, and then use that to find the t. So you're actually not going to look up the t until the very end. You're going to actually calculate the t from the r's you look up and the third law. And then finally, the one question for the lab is to take the t's that you calculate and compare that to the actual values, which you can get out of the same places you find the r's, and see how close you get. And you'll find out that you're pretty close. So that is lab 2.